Today we're going to start talking about organic chemistry and alkanes. Organic compounds are just my absolute favorite. This is my favorite branch of chemistry, and I love talking about studying organic compounds. So the big idea here is that alkanes, the simplest organic compounds, are mostly unreactive, and they are generally not generally found in the human body. So straight chain alkanes are not usually found in the human body, but a lot of other organic compounds are. And a lot of other organic compounds are super common in nature. For example, here is the structure of fructose. So fructose has the CH2OH and then a C double bonded O, and then there's a C with an OH that's in our perspective on the left side, and then a C with an OH on the right side, and a C with an OH on the right side, and then it ends the bottom of the chain with CH2OH. And so all that's going to be important. All of those OH functional groups, for example, are alcohols that are really important. And fructose is found in things like apples, right? It's a simple sugar that's found in apples. So we're going to study carbon-based compounds. The simplest alkanes, again, generally unreactive, generally not found in the human body, but a lot of other organic compounds are important to the human body and important to biochemistry. And sugars like fructose for energy are really important. Okay, so again, organic chemistry is just all about carbon. Carbon's got 4 valence electrons, and so therefore it's always wanting to go out and make 4 bonds. So, if my carbon atom has 1, 2, 3, 4 valence electrons, then it wants to go out and share those valence electrons with other atoms, and it wants to be able to make 4 bonds. And so a covalent bond is wherever you have 2 electrons that can be shared. So when I'm drawing bonding, I like to just draw the 2 atoms of the covalent bond, the 2 electrons of the covalent bond, and then literally kind of cover them up as I'm making that bond. It's just how I remember that everyone's, donated the electrons to make that covalent bond. So hydrogen has 1 valence electron. So if a hydrogen atom has just 1 valence electron, then it just wants to go out and make 1 bond with something else. For example, with our carbon here, if hydrogen has 1 electron and carbon has 1, they can make 1 bond. And so a carbon surrounded by 4 hydrogens like this is our simplest alkane, and it's just called methane, which is the natural gas that we use in our everyday lives to heat our homes and heat our hot water heaters. And if you have a gas stove or gas fireplace, then you burn that natural gas or that methane. Alkanes will contain all single bonded carbons. And those carbons are, each going to have 4 bonds as well. And so you'll have a CC with a single bond. In an alkene, you will have a C double bonded to a C. And then each of those carbons will be able to go and make 2 more bonds. In our alkane, each carbon can make 3 more bonds here. And then in our alkyne, we'll have a CC triple bond, where each of these carbons in the triple bond can each make, 1 more bond to another atom. So they go ene, ene, ine, single, double, and triple bonds, and they're just, I remember them because they're in alphabetical order, those endings, ene, and then ene, and then ine, for single, double, and then triple bonding. Now let's just take a look at our periodic table for a second, and you might want to get yours out right now too. Again, carbon was right here. Carbon has 6 total electrons, but 4 of those were valence electrons. Now just to kind of remind you, if we were drawing a Bohr model, and carbon would have 6 protons in a nucleus, and then it would have 2 electrons in a first energy level, and then its second energy level, 1, 2, 3, 4 electrons. So those are its 4 outermost valence electrons. So when we're drawing carbon with its 4 valence electrons, it's because the first 2 really don't matter. They're in that filled shell. They just don't matter for reactivity. They won't be involved in chemical bonding or chemical reactions. Now, what if we look at some other elements that we'll need in organic chemistry? We'll need our hydrogen with its one valence electron, so it likes to go out and make one bond. We'll need nitrogen and oxygen. Those are going to be important. So nitrogen has 5 valence electrons and oxygen has 6 valence electrons. And so if we just kind of review those, if we draw a nitrogen with its 5 valence electrons, we put them around it like a clock. So 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock, 12 o'clock. We have 5 dots around our nitrogen. The 3 that are unpaired, the one at 3 o'clock and the one at 6 o'clock and the one at 9 o'clock, those are the ones that can go out and bond with other atoms. For example, if they bond with a hydrogen, their valence electrons can get together to bond with 3 hydrogens, and we'll make ammonia, or NH3. And then lastly, oxygen here has 6 valence electrons, so 12, 3, 6, 9, 12, 3. And then if we go to those 2 that are unpaired, we can go ahead and share them, let's say, with 2 hydrogen atoms. And lo and behold, we have water, right? So oxygen has 6 valence electrons, but because of the way we, draw them, 2 are unpaired, and then it can make 2 bonds. So nitrogen, 5 valence electrons, makes 3 bonds. Oxygen, 6 valence electrons, likes to make 2 bonds. And then the last one we might use some is the halogens. And so the halogens are in the second to last column on the right on the periodic table, and they all had 7 valence electrons. And they were fluorine and chlorine and bromine and iodine as we go down that second to last column. And so let's say we take an example like chlorine. We might use quite a bit. In organic chemistry, it has 7 valence electrons, so we'll put one at 12, 3, 6, 9, 12, 3, 6. And we'll have this one unpaired valence electron. That's the one that can go out and bond. So that's the one that will form covalent bonds. So when we have a halogen on the chain, it's going, in a carbon chain, for example, it will make 1 bond. Okay, so I thought that little review, hopefully, of the periodic table and valence electrons is helpful. And, we'll use that to go ahead and just recap right here how many bonds each of these atoms wants to make. So let's first talk about valence electrons. For carbon, we said carbon has 4 valence electrons. Hydrogen, we said, had 1. Oxygen had 6, nitrogen had 5, and each of the halogens had 7. So if we go and we draw a dot structure for these, this will be our Lewis dot structure. Our Lewis dot structure for carbon has 4 dots around them, 1 at 12, 3, 6, and 9 o'clock. Hydrogen is just going to have 1. Oxygen is going to have 1 at 12, 3, 6, 9, 12, 3. Nitrogen is going to have 12, 3, 6, 9, 12. So it has 5 total valence electrons. And then the halogens, let's do chlorine as an example. Again, it has 7 valence electrons. So because carbon had 4 valence electrons and they're all unpaired, it wants to make 4 bonds when it's bonding covalently. Hydrogen's just got that 1 electron, so it's going to make 1 bond. Oxygen has these 2 unpaired valence electrons and will make 2 bonds. Nitrogen with the 3 unpaired valence electrons likes to go out and make 3 bonds. And then halogens like chlorine or fluorine or bromine or iodine have 1 unpaired electron and want to go out and make 1 bond. I don't know why I put an S on that. That was kind of silly. So I'm trying to get my eraser, but it doesn't want to let me do that either. So we're just going to scribble it out. It makes 1 bond. All right. So that concludes just our first little introduction into the elements that we're really going to use a lot in organic chemistry and the main types of bonds that we're going to have, those single, double, and triple bonds with alkanes, alkenes, and alkynes. And to just sort of wrap that up, I just kind of remember the ANE ending is going to have a single bond, one line. The ENE ending is going to have a double bond, two lines. The YNE ending is where I will have triple bonds, so that's three bonds between carbon atoms. So ene, ene, and yne, single, double, and triple are in alphabetical order. So it's really helpful if you just kind of look at the A, E, and Y in alkane, alkene, and alkyne, and it can help you keep those straight.